Hello, my name is Graham Robertson. In 1977 I failed a PhD in the philosophy of science at Cambridge University and was not given leave to resubmit a revised dissertation. The title of the thesis was Philosophical Problems of Quantum Ontology. So I'd like to thank the Scientific and Medical Network for this opportunity to redeem myself a little and explain my understanding of quantum theory a bit better. The talk is called The Quantum Complexity Behind Quantum Reality. It is divided into three parts: an outline of the essentials of quantum theory, a discussion of some glaring problems of interpretation, and my shocking philosophical conclusions. In 1900 it became clear to Max Planck, and in 1904 it became even clearer to Albert Einstein, that radiation transfers energy in quanta of definite amounts. Radiation behaves like a stream of particles of energy E equals h nu, where nu is the frequency and h is a tiny constant, 6.6 times 10 to the minus 34, Planck's constant. For a given frequency, each quantum is a definite amount of energy. In 1913, in order to account for atomic spectra, it became clear to Niels Bohr that angular momentum L changes in precise jumps, L equals nh bar, where n is a positive integer, and h bar is defined as h over 2 pi for convenience. In 1925, Werner Heisenberg altogether abandoned the notion of microscopic particle trajectories and represented position and momentum by transformation matrices X and P, leading to matrix mechanics. Meanwhile, in 1924, Louis de Broglie proposed to let particles assume wave properties by assigning momentum P equals h over lambda, where lambda is the wavelength. He proposed waves of the form e to the minus I et minus p dot x over h bar. By an amazing leap from the ordinary waves of the form e to the minus I omega t minus k dot x. Up to then, most physicists passionately believed that light was a wave phenomenon and that massive particles were not waves. In 1925, Erwin Schrödinger replaced position and momentum variables in the equation for time-independent total energy, E equals kinetic energy plus potential energy equals p squared over 2m plus v of x, with operator x times and differential operator minus I h bar d by dx acting on a wave function, which is usually denoted by psi of x, minus h bar squared over 2m d2 psi by dx squared plus v of x times psi equals e psi. He also represented time and energy with t times and I h bar d by dt, giving a time-dependent equation for psi of x and t. This approach is called wave mechanics. Minus h bar squared over 2m d2 psi by dx squared plus vx psi equals I h bar d pi by dt. Both these equations were incredibly successful at reproducing the hydrogen atom spectrum, although the ontological meaning of the wave function, which changes causally in the wave equation, was and still is extremely unclear. The origin of this choice of operators can be understood by way of a Fourier transformation. In 1928, Paul Dirac formulated a relativistic wave equation, which incorporated intrinsic spin and accounted for the hydrogen spectrum fine structure. The Dirac equation unexpectedly predicted antimatter. Dirac found a way to square root and quantize e squared over c squared minus p squared equals m squared c squared. I h bar gamma mu d mu psi equals mc psi. Matrix mechanics, wave mechanics, and Dirac theory are unified in functional analysis, where psi is a vector or ray in Hilbert space, whose basis vectors psi I are functions and whose scalar elements alpha I are complex numbers. Vector spaces evolved from rectangular 3D ijk axes to curvilinear 3D EI, EJ, EK axes to n-dimensional orthogonal functions, sine x, sine 2x, sine 3x, for example, to psi equals the sum over I, alpha I, psi I, where alpha I are in the field of complex numbers and psi is in a Hilbert space. In quantum theory, self-adjoint Hermitian linear operators A, for example, represent observables, and they project real values AI from basis states psi I. So AI acting on a function psi I is equal to a number AI times psi I, where AI is in the real field of numbers. This is the eigenfunctions and eigenvalues equation, which is central to quantum theory. Eigen means the same, since A leaves this state unchanged. So these are states where this observable, when it acts on this state, projects out a real number but leaves the state unchanged. The superposition principle says that linear combinations of solutions to Schrödinger's equation are also solution. So if I observe A on some superposition of states, alpha 1, psi 1 plus alpha 2, psi 2, then that acting on this gives alpha I, which is just a number, AI, A1, psi 1, again A1 is a real number, plus alpha 2, A2, psi 2. Like ordinary waves, only one eigenvalue and its eigenfunction is actually realized on measurement, thus affecting a collapse of the wave function from A1 and A2 to A1 or A2. Superposition and is only valid if there is no way to know, even in principle, which result, if any, actually happened. Therefore, causality only applies to unobserved systems. In 1926, Max Born realized that the probability of getting result A1 is given by alpha 1 squared, and the probability of getting A2 is alpha 2 squared. Psi's are normalized to 1, and alpha 1 squared plus alpha 2 squared has to equal 1 to conserve probability. Note in passing that the local U1 gauge invariant transformation psi goes to e to the I theta times psi leaves modulus of psi squared, and therefore all predictions unchanged, because psi star psi goes to e to the minus I theta psi star times e to the I theta psi equals psi star psi, because the e to the I thetas cancel. And notice the thetas can be functions of x as well here. This fact, when exploited, miraculously yields electromagnetism and even the basics of the standard model of particle physics with gauge invariance U1 cross SU2 cross SU3. In 1922, Theodore Kaluza also miraculously showed how to produce Maxwell's equations from five-dimensional general relativity. These ideas, gauge invariance and five-dimensional general relativity, are fundamental to string theory, which needs 26-dimensional general relativity to quantize it, and a lot of gauge invariant symmetry, E8 cross E8, to tame it. Back in 1888, Schwartz proved mathematically an inequality which leads to a relation between the standard deviations of two self-adjoint linear operators A and B, saying that the products of their standard deviations in some state psi is no less than half of the modulus of the mean value of their commutator. So the standard deviation in state psi of A times the standard deviation in state psi of B is greater than or equal to half the modulus of the mean value of the commutator of A and B, that's AB minus BA. In 1926, Heisenberg realized that his matrices didn't necessarily commute, because the order in which certain pairs of observables are measured could affect the outcomes. He found that the commutator of his position and momentum matrices is actually a constant times the unit matrix, x p commutator equals I h bar. This may be verified using the differential operators x times and minus I h bar d by dx in some general state psi. So the commutator of x and p on psi is that where the derivatives cancel, leaving I h bar psi. Then employing the Schwarz inequality immediately led Heisenberg to his famous uncertainty principle, delta x delta p is greater than or equal to h bar. In the same year, Heisenberg's revelation led Bohr to the concept of complementarity, which attempts to justify the implication that a fully prepared pure wave function psi contains everything relevant that we can possibly know. There are basic limits on simultaneous knowledge of two non-commuting observables. There are three fundamental mathematical objects in linear algebra: operators and their corresponding eigenfunctions and eigenvalues. In quantum theory, an operator embodies some particular observable and acts like a measurement on a system. If successive measurements always reproduce the same measurement result, then the system is said to be in an eigenstate, eigenfunction, of that observable's operator. Each eigenstate is associated with a real rational number, or eigenvalue, whose value is one possible result of the measurement. After each measurement of an observable, the Schrödinger equation may have to be solved again, or the system may have to be prepared again in the same original state, unless it is in an eigenstate. In practice, a measurement is usually considered to be an irreversible act of amplification. However, it is believed that a superposition is only valid if there is no way in principle to know the result of the measurement. If information which is apparently lost in the collapse of the wave function is accessible in principle, then the interaction is insufficient to destroy the possibility of interference, and the measurement is therefore not actually a measurement at all. So in summary, the introduction of complex valued functions and non-commuting observables implies inescapable uncertainty, and that implies the necessity to talk in terms of probabilities, which in turn implies the need for an epistemological collapse, if not an ontological collapse, of the wave function. In December 1926, Einstein famously wrote to Born, saying that God does not play dice. Einstein demanded determinism. Still, Bohr continued to argue that particles do not have well-defined properties until they are measured. To which Einstein quite understandably responded, "How does the universe know someone is measuring something?" And later, to a friend, "Does the moon exist only when I observe it?" In 1935, Einstein, Podolsky, and Rosen wrote in Physical Review that in a complete theory there is an element corresponding to each element of reality. If one can predict with certainty the simultaneous values of position and momentum of a particle without in any way disturbing it, then that should prove the need for hidden variables in quantum theory. EPR described a particle splitting into two parts, which then fly apart. If someone measured the momentum of one part, then the momentum of the other would be known exactly by conservation of momentum. And if one measured the position x of the first part at a certain time, then the position of the second would be known exactly minus x at that time. Thus, EPR argued that quantum theory is manifestly incomplete because x and p clearly both exist simultaneously exactly. But in 1964, John Bell considered two spatially separated entangled particles which had once interacted as described by EPR. The particles appear to have correlated properties such that measuring one instantaneously affects the state of the other. Bell proved via an inequality that if quantum theory is correct, then certain predicted correlations defy classical intuitions about causality and locality. Quantum theory is at odds with the assumptions of local realism, no instantaneous effects, and the existence of determinate local hidden variables. Bell intended to eliminate the observer from physics, as was the desire of many other physicists and philosophers such as Henry Margenau and Karl Popper, but Bell failed. In 2022, John Clauser won the Nobel Prize for consistently violating Bell's inequality and numerous experiments since 1972. These results suggest that the correlations between entangled particles are inherently non-local and cannot be explained by any deterministic model. By the way, this doesn't conflict with special relativity. Further, in 1967, Cochrane and Specker published a proof that there is no way to assign well-defined values to certain properties of particles in a consistent realist manner that is independent of how they are measured. More precisely, there can be no hidden variables that determine behavior independent of the measurement context. You can't easily embed a quantum logic in a classical logic. Meanwhile, back in 1926, Schrödinger declared, "If we are going to stick to this damned quantum jumping, then I regret that I ever had anything to do with quantum theory." Schrödinger hated the notion of collapse of the wave function. In 1935, Schrödinger produced his cat to illustrate the paradox of superposition. The cat can't be alive and dead at the same time. It doesn't accord with everyday experience. Of course, the necessity of keeping a cat alive in total isolation from its surroundings is already a monumental feat, as the makers of quantum computers well know. However, in 1999, Marcus Arndt demonstrated quantum interference with buckyballs, each made of 60 carbon atoms. In 2010, physicists at Santa Barbara built a tuning fork the size of a typical computer screen pixel and put it into a superposition. In 2020, physicists at MIT showed the effects of quantum fluctuations in laser light on a 40-kilogram mirror. The fluctuations moved the mirror a measured 10 to the minus 20 meters. It was for a graviton interferometer. Also, superfluidity and superconductivity show that quantum effects are not restricted to tiny particles. So where is the division between quantum and classical realms? In 1961, Eugene Wigner proposed that a friend covertly observes a supercat. Wigner then considered whether he could believe that his friend was in a superposition of states right up until he was asked the big question, is the cat dead or alive? Wigner concluded that his friend's consciousness already must have collapsed the supercat even before he was asked. Meanwhile, in 1952, Bohm developed a hidden variable theory which restores particle trajectories and determinism. Sounds good, doesn't it? In his theory, particles are guided by the Schrödinger wave and are controlled by an additional complicated energy potential. However, the theory, while being ontologically more comfortable, gives no predictions different from quantum theory, and it is non-local too. This approach is reminiscent of early reactionary attempts to rescue Newtonian gravity from general relativity by significantly complicated Newtonian gravitational forces. It can be done, but it is unsightly. Everyone tries to preserve treasured concepts like reality, but Bohm later significantly changed his tune, as did Schrödinger. In 1957, Hugh Everett, also known as the Everett-Wheeler-Graham theory, proposed the many worlds interpretation, not to be confused with the multiverse. It is deterministic and local at the expense of an infinite number of worlds. Sean Carroll estimates there are only 10 to the power 10 to the power 122, which is over a googolplex. A Google is 10 to the 100, and a Googleplex is 10 to the Google. Everett, Wheeler and Graham claimed that there is no collapse. There is never any collapse. Every possible outcome of a measurement is realized in some metaphysical world somewhere. You are in this one with me. This is introducing any amount of stuff just to retrieve pseudo-determinism, because no predictions of quantum theory are changed. Causality of the Schrödinger evolution is the determinism of this manyverse. In 1981, Gherardi, Rimini and Weber proposed a spontaneous collapse theory in order to regain classical realism and prevent macroscopic superstates. It claims that collapse occurs randomly at a rate of about 10 to the minus 8 times per second in any small volume of around 10 to the minus 15 cc's. This mechanism introduced absolute randomness in order to fix something else, reality as we know it. In recent years there has been much hope that the concept of quantum decoherence, introduced by Dieter Zeh in 1970, will solve the measurement problem, namely the collapse of the wave function. This approach argues for the appearance of wave function collapse by loss of coherence or information to the environment, like frictional losses or like dissipation of water waves. But without any collapse, the wave function in its frictionless domain of mathematical purity never forgets, meaning that all that seems real in principle may be undone, since no interference effects are ever finally lost, even in big things with 10 to the 23 atoms. An example is John Wheeler's delayed choice quantum eraser. In summary, there have been many attempts to rationalize quantum theory or replace it with something better, but nothing can improve on the fabulous mathematical successes of quantum theory, and none of the various proposed interpretations of quantum theory is totally convincing. On the negative side, David Merman just said, "Shut up and calculate." On the more poetic side, Aristotle said, "Each thing is a kind of unity, and potentiality and actuality taken together exist somehow as one." Consider the metaphysics of Immanuel Kant, 1724 to 1804. He attempted to reconcile the two current conflicting theories of knowledge of the 18th century, that of the British empiricists like Locke, Berkeley and Hume, who believed knowledge came from perceptual experience, and that of the continental rationalists like Descartes and Leibniz, who believed knowledge came from reason alone. Kant concluded there are two sources of knowledge, sensibility and understanding. For Kant, there are two epistemological levels. There is a phenomenological level, which reveals a contingent sequence of events, which is our everyday world. There is also a transcendental level, which holds an a priori scheme of causation of things in themselves, noumenal objects of pure thought that we cannot know. Consciousness for Kant is the synthetic unity of the manifold of perceptions. Now identify eigenvalues with the ordinary world of phenomena, of real measures, of ordinary experience. All is real. Identify eigenfunctions and wave functions in general with the world of noumena, things as they are in themselves, independent of sensory perceptions and cognitive faculties, and beyond the reach of human cognition. Kant's noumena sets boundaries on what can be known by human cognition, a bit like the limitations of the wave function. Further, the mathematical operators and the related devices that we construct or have to observe with fit well with Kant's notion of forms of perception. In particular, the five senses provide the fundamental structure or framework through which we experience reality. Kant added in the forms of space and time. Along with the forms of perception are the categories of understanding, the fundamental concepts through which we understand and interpret sensory input. Kant argued that our knowledge is actively shaped and organized by our forms of perception and categories of understanding, a bit like the quantum operators that represent observables and define meaning by the experimental arrangement. So, returning to the primary conceptual problems of quantum theory, where and when does the collapse of the wave function occur? Is it at the first macroscopic object in the von Neumann chain of amplification, as Bohr and Heisenberg originally assumed? Or is it at the first conscious observer, as Wigner and von Neumann first thought? Or, if quantum theory is a universal theory, isn't it the case that the only obvious place for a split to be is at or in myself, in oneself? Consider carefully the nature of consciousness. How many consciousnesses are there? As many as there are living, awake human brains? No. Consciousness is singular. Consciousness is this immediate experience one is having right now. If you think differently, then just take this as my definition of consciousness. As far as I'm concerned, consciousness can't be put in a bag and sent to China unless I get in the bag. One's immediate awareness is consciousness, no more and no less. Consciousness is always here, never there. It is always now, never then. Ours is the only consciousness we do or can experience. If you are following me in this argument, then you should agree that you can immediately, empirically verify that there is only one consciousness in the universe. I submit that the only collapse is at or in oneself, at that empty space between nothing and something, oblivion and vigilance. When one opens one's eyes and ears, the whole universe collapses immediately into a complete and consistent reality. It silently and continually snaps into one's reality from a kind of collective unconscious, a wave function, a quantum complexity. You create reality by forcing a phenomenal world out of the noumenal world by application of your senses, innate or extended. The noumenon binds us together into a consistent, irreducible whole, so that there can be no contradictory evidence in truth. One is back after 500 years of Copernicus at the center of the universe. So because the wave function is complex, ignorance is theoretical. That is, one is necessarily ignorant of so much. Because superposition is intangible, interphenomena are not objective, that is, between phenomena are only noumena. Because every experience is derived from a pure universal state, one is complete sense, and the best one can possibly do is to have a balanced set of complementary senses, physical and mental. One is the perfect observer, not God. Because probability is fundamental and inescapable, are we free? This is an important question for moral philosophers. Might we be able to harness through the quantum Zeno effect the freedom that we actually feel? Really, might we? Zeno argued that a flying arrow actually never moves, and Aristotle concurred with if all that occupies the same space is at rest, and if that which moves occupies such space at any moment, the flying arrow is at rest. Cynically, we might add, and the watchpot never boils. Also, we might want to complain that the infinite series 1 plus a half plus a quarter plus a eighth, etc. is only and exactly equal to 2, no more, because some infinite series are finite sums, and therefore the arrow can move. Anyway, according to the quantum Zeno effect introduced in 1974 by Fonda and Ghirardi, by continuous repeated observations one can effectively freeze or slow down evolution of the noumenon, which evolves through the Schrödinger equation. At the level of the nervous system, one can imagine that such control of just one important nerve might be sufficient to gain macroscopic control of something big and useful like a finger. I attempt to elaborate on this kind of thing in my book, Unity Consciousness and the Perfect Observer, which was self-published in 1995 and is available for £5 or as a free PDF from my website at robertson.uk.net, where you will also find the script for this talk plus a few random extra notes. Beware, my website has no security certificates, but don't worry because there is no way to enter any data, so you're pretty safe. And your antivirus may complain, but there are no known viruses in any of the files or executables that you might download. My coding is in APL characters, which are a wee bit weird and suspect from the point of view of most antivirus software, hence alerts. Also beware if you're philosophically or politically correct. Thank you so much for listening.